So if you look at this corrective assignment, the first thing you should notice is those formulas. And we had a warm-up a couple classes ago where we wrote down all of the formulas. Make sure that if there's something here that you don't have on your study list, that you kind of add that to it, because you want a nice reference sheet for you to know with the things that may or may not be given to you. So the Pythagorean theorem, I think we're pretty good with. Triangle, maybe the cone is new to you. The sphere, 4/3. There's actually a pretty cool geometry lesson that I like to do. It shows you the relationships between the cone and the sphere. Conversations. I don't bother memorizing area formulas for things like cylinders, because to me it's just the sum of the areas of all the sides. So when we're talking about that surface area of a 3D shape, I just rely on my other formulas that I know. What happens with these kind of related rates problems is you begin to become almost a detective, where you're looking at, okay, what did they give me? And is it something that I need or not? Or do I have enough tools to find a missing value? So I want to talk about two really quickly. They gave you this basic formula for whatever it represents. And when you look at their values that they gave you, I know that B has a value of -2, C has a value of -3. Then they go ahead and they tell me that the change in A with respect to time is equal to 6. But notice they never told us what A was equal to. We have enough information to find it. So if they're going to withhold something like that, and that can be a kicker that holds you down the end when you start taking your derivatives and looking for your related rates. But if I have this rule, I can go ahead and plug -2 and -3 in for B and C and find that value for A, which, correct me if I'm wrong, ends up being the square root of 2, correct? When we look at each of these rates, it gives us the rate of change of A, it gives us the rate of change of C with respect to time, but you'll notice it doesn't give us the rate of change of B, and that is because that is what we're solving for. So if you end up struggling to keep track of what you're given and what you know and what you should be able to find out, maybe sometimes making a chart of these values before you go diving in, because this is what I'm solving for here. And I may have thought that that was an unknown, but it wasn't. I just needed to go get it. Are we good with 1 and 2? Do anybody need to see them? Are we okay with those? When you get to these, you almost get into this mind frame where you're like, oh, this is a Pythagorean one. Oh, this is an expanding circle. Oh, this is a shrinking circle. Oh, this is a balloon or a rocket or whatever is going up in the air, and I'm watching it go. So we expose you to so many types that when you approach a problem, you should right away start categorizing it. Oh, is this Pythagoras? Is this an angle of elevation? Is this a shrinking ice cube, a melting ice cube, or whatever? When we're talking about a ladder, one of the things that we want to make sure that you remember most likely with the ladder is its constant. So you begin real quickly when you have your A squared plus B squared is equal to C squared. Once you've taken this derivative enough times, once you've taken this derivative enough times, you remember those 2's always cancel out, and you're always looking at whether or not this is a constant. And the value doesn't go to 0, but this rate does, because the rate of change of a constant is always going to be 0. So be careful you don't take too many shortcuts, because the value of C is not 0. C has a value, that ladder's 25 feet long, it's just not changing. With these conversations, what I want you to picture is, think of these related rates as a movie where we're talking about having this ladder slip away, and I'm pausing the movie at that moment to figure out how much the ladders, or what the rate of change is. So if I have a grass and I have a house and I have a ladder, as this ladder is spinning and sliding away on down, there's going to be a moment in time where this height has a value. And a lot of times when we figure that out, we need to freeze that video and go get that value using our original equation here. So the ladder 25 feet long is leaning against the house. The base of the ladder is pulled away at a rate of 2 feet per second. So if I have and when you label this, I always get into the habit of labeling my horizontal movement A, my vertical movement B, and my hypotenuse is always going to be C. If that's a habit, a discipline that you get into, then you don't get tangled up in your DAs or DTs. A lot of times I'll also label my diagram with my rates and my arrows. So the base of the ladder is moving across this way, and my change in this with respect to time is going to be 2 feet per second. It helps me when I draw arrows because I know that this rate, this change in my B with respect to time has got to be negative because it's decreasing. So picture that movie in your head of what's happening and what rates might be positive or negative. So how fast is that top moving down the wall? When they give you this conversation, when the base of the ladder is 7 feet from the wall, that's that moment where we pause the movie. Now, okay, so now when A has a value of 7 and C has a value of 25, I can come over here and do my Pythagorean theorem, kind of like how I had to use the other one to figure out that A value. Right now, A has a value of 7, so that's 49. B, I'm not sure. C is going to be 25 squared. So now I can solve for B. Anytime I have one unknown, now I can go get B. So freezing that moment of time lets me go solve for B. And then when I go to plug in, you'll find that you have everything that you need. You have an A value. Here it is at 7. You have the rate of change of A. Here it is at 2. You have your B value. We solve for it here. Your rate of change of B, that is what you're looking for. How fast is it moving? I don't know. But then I have this C over here. So it becomes this exercise of going through and looking at what we see, drawing the picture, making an organized list of your values, using the original equation to figure out what you need. Those are all strategies that help you get better at doing this. Any questions on the front of this? Were you okay with the area one? Did you forget your 1/2? Don't forget area's 1/2. This is a triangle. A couple people asked about the planes flying. So when I have the one plane is flying this way and the other plane is flying this way, they're on track to meet each other at a right angle, and I'm looking at the distance between them and how they're getting closer and closer together. So I can see that right triangle there. Anybody want to see 4 or 5? Do you want to do the angle of elevation one with the balloon and the tray? Yeah.
I was just curious, for number 4, there's no constant, right?
No, there's not a constant because everything's changing. So this airplane, here we go again with my starfish. I'm just gonna draw this. Restore. This airplane is flying this way at a rate, and this airplane here is flying this way at a rate. So this distance between them is shrinking. So you have all 6 values that you have to take into consideration. No easy outs with a constant. Would you like to do the trig one? Okay. So a balloon rises at a rate of 2 meters per second. So we'll give our little purple balloon. So there's our balloon, and it's rising at a rate of 2 meters per second. So what does that tell me? That means that dB dt is equal to 2 meters per second. From a point on the ground 30 meters from an observer. So here's our grass, and here's our observer. And I know that this is 30 meters. And this one's going to be an easy one for me because that's not changing. He's not moving. Find the rate of change of the angle of elevation. So when the balloon first started off down here, he was looking at it, but as the balloon's gone up, 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 his angle of elevation is changing as he's watching it, and we're going to call that our theta. And what I'm looking for is find the rate of change of my angle of elevation. So that's going to be my change in my angle with respect to time. And the moment I'm watching this happen, I'm watching the balloon go up, and I'm wondering how quickly is that angle changing as the balloon is going up. And then I'm going to freeze, like, ready now. That's when I pause or freeze the video, because I'm going to care about it when the balloon is 25 meters in the air. So I know how quickly the balloon is going up at a rate of meters per second. I know how far away I am from the balloon, and I have set up where I'm looking for the rate of change of this. So this puts me in a position of needing to do trig. I'm looking at tangent because it's my opposite over adjacent. You okay with that? So I know that the tangent of theta is equal to my opposite over my adjacent. I can simplify things a little bit. I know my moment of time, but this is changing, so I'm not going to fill in 25 yet. But is my observer always 30 meters from this? So this ends up being a constant. And because this is a constant, it's not changing. So when I'm looking at taking the derivative of that, I don't have to have two, like an x over a y or an a over a b, because my adjacent side is always going to be the same. So if I wanted to, I could rewrite this as the tangent of theta is going to be 1/30th. Ooh, that was weird. I don't know why I did that. Is going to be 1/30th of my side opposite, and I'm going to go ahead and call that B, because I'm into the habit of using my A and my B and my C to just help me with that conversation. All right, so let's go ahead and just dive in and take the derivative. So the derivative of tangent is going to be secant squared of theta with the change in theta compared to time. So that's going to be my derivative of that value. And then when I look here, I'm just going to have 1/30th, and then this is going to be dB dt. And that simplifies things significantly. that simplifies things significantly, so you don't have to necessarily do the power rule or the quotient rule. Meanwhile, if this guy was walking, keep in mind, if this guy is walking and you wanted to know as he's walking and the balloon is going up, you could figure out that change in the angle too. It's just a much more complicated problem. So he could be walking. You can walk and look at something as you go. That's possible. They made it simple for us, so it's not. All right. When we go to fill in these values here, keep in mind, this is what we're solving for. So at some point, we're going to need to know what that theta is. What is that angle at that moment of time when we're freezing this here? So what we'll do is we'll go ahead and do some inverse trig, because I know that the tangent of theta is going to be equal to my opposite over my adjacent 25 30ths. So that means that my inverse tangent of 25 30ths is going to equal to my theta. When you open up your calculator, for all things calculus, you want to make sure that you are in radians. The geometries will change the calculators to degrees because they don't know about radians yet. And if you don't know the difference between radians and degrees, it's like centimeters and inches. It's just two different ways of measuring the same thing. So 360 degrees around a circle was a really pretty number that was divisible by a lot of things, so they were able to just make it up and say, I call this 360, therefore this is 180 and this is 90, and everyone's like, well, that's a nice number, that divides evenly, we like it, hooray, good for you. But that's the same as the 12 inches that the king said was his foot is a foot. You know that we call it a foot because that was the size of his foot at that time, right? So arbitrary, made up, now we're going to use it. The metric system just makes so much more sense, which is why we switch from standard to metric as much as we can. Radians makes so much more sense when you look at the unit circle. If I have a circle with a circumference that is going to be pi times my diameter, if my radius is 1, then you see how I get 2 pi all the way around, which is how I get pi. So we measure everything in radians in terms of pi. Little history lesson, but we want to make sure that we are in radians. So you're going to go and use your inverse tangent function. Hey, calculator, tell me the tangent of this ratio between opposite and adjacent. And it tells us that that theta value was equal to what? 0.69. We can do, usually trig we do 6947. All right, so you don't have a secant on your calculator. So at this next point, I'm going to go ahead and call it 1 over the cosine of that theta, and I want to make sure then I square that theta, and that's going to be times the change in theta with respect to time, which is equal to 1/30th times the rate that my balloon is going up in the air, which is 2. And then this theta here is what you're going to put in there. So if I go back to my calculator, I'm going to leave that value in there because that's my rate, or that's my radian, my angle value. So in order to solve for the change in theta with respect to time, I have a 1/15 times the cosine of that theta squared. So I'm going to go ahead and put that theta in with my calculator. So I know that the cosine, and I can do second answer, and it'll plug this answer in. is that, and then I want it squared is that, and then I want it divided by 15, and I get that value. That's how much is changing. 0.039. Everybody okay with that math? So make sure you include your units. The rate of change is 39 tenths, hundredths, thousandths, 39 thousandths radians per second. Does that answer your questions? Okay? Pretty good? Okay. So make sure that, in fact, I saw some of you doing this while you were doing your warm-up. It was nice to see some of you go back to your packet, because those practice ones, if you don't understand why they use the values that they do, you have to ask. Because again, these are all just sample problems. Can you do it like this? Can you do it like this? Can you do it with a constant? Can you do it without a constant? Can you do it when you need to figure out another value? All those things. Okay. The next two lessons have nothing to do with related rates. So we spent 2 days on related rates, we're done. Like now you're an expert on related rates. So what we're talking about in the next two things is another application of using the derivative. And with this one, it's a concept of talking about approximating a value when you have something called local linearity. So when we have the tangent line of a function, we can give you that approximate value if that value is super, super close. So what I want you to imagine is us doing all this work and being able to figure out the equation of the tangent line, but not really understanding or having a picture of the equation of the graph. What we can do is say, because that we know there's that point of intersection, and we know that that tangent line is so very close, that we can use that tangent line as estimates for what the input-output values of the function are. And it also has a conversation with concavity when you're talking about something being concave up or concave down. So did you talk about concavity in Algebra 2 and Pre-Calculus? Concavity has to do with the shape of the curve and how it's bending. It's up like a cup. A parabola is concave up, they say, because that concavity is shaped like that curve. If something is concave down, it's down like a frown. So think about if a parabola was negative, and we had the opposite of y is equal to x squared, that would be concave down. So when we have something that's concave up like a cup, we can have a tangent line, and that tangent line, no matter where we decide to put it, and what I want you to do is slide your pencil around, because if the shape is concave up like a cup, your pencil is always under it. Does that make sense to you? So any estimate that we get of a value that's sitting on this tangent line is going to be an underestimate of whatever input-output value exists on our curve. If I have a tangent line and I have a concave down shape, having a hard time here, and I have a concave down shape, then no matter where this tangent line is, because my graph is concave down, my tangent line is always going to sit on top of it, so it's always going to be an overestimate. So I just drew two tangent lines there, but play with it and slide your pencil around the whole graph so that you can see where it's a overestimate and underestimate. So anytime that we have a concave up, and if you want to do our little rhyme, so that you know that it's concave up like a cup, then this tangent line the values will be an underestimate. If I have a shape that's concave down, and again you can, like a frown, then your values that are on that tangent line will be an over estimate. Now in this first one that they give us, they end up giving us, you know, like here we have a value of the function, and we need to know that like this rule, this application of using the derivative, using the tangent line would be when we don't have that curve and we need to be able to use an estimate to get values. Go ahead.
So when you say overestimate and underestimate, do you mean that as in the tangent line, the like definition of the tangent line is that it's an underestimate, or do you mean like the values are
The values, the input-output values. So let's say a story where here is our graph and you really want to know, like let's say that here's our graph f of x, right? And you really want to know this value right here. You want to know this value, but you don't have an equation of the graph and you have no way of figuring that out. You can use the tangent line and you can recognize that I can figure out an input-output on the tangent and it'll be super close, but it'll be lower. It'll be an underestimate of what that true value is. Same thing over here. If I'm looking for this value right here, but I can't find it, you can say, hey, I know, why don't you go ahead and use the tangent line equation, but that's going to be a little higher than what you need because your shape is concave down. Does that clarify? All right, good. All right, so let's take a look at this first one. My function is concave up on its domain. So we'll just go ahead and draw a little sketch like that. So you know, there's our shape that's concave up on that domain. I know that the input value at 4 gives me an output value of 5, and that the instantaneous rate of change at 4 gives me, or is 3. If I want to know what is an estimate for something super close to this, using local linear approximation for f at f of 4, what would that look like? So what I'm going to do is I'm going to find my equation of my tangent line. So if I already have my slope here, I know that I can do y minus y1 is equal to m times x minus x1. I can figure out my equation of my tangent line and use that equation with this input value to go ahead and do that approximation, because I know that the more I zoom in, I get closer and closer to that being a linear conversation. All right, let's talk about what we have. F is concave up on its domain. Here's an input-output value that I have. So I know I can say that y minus 5 is going to be equal to that slope times x minus 4. And at 4, my rate of change is equal to 3. So there's my equation of my tangent line, where I have y is equal to 3x, what's that, minus 12 plus 5 looks like minus 7. So this ends up being my equation of my tangent line. And then I can go ahead and use that equation to help me figure out what the local linear approximation for f at x is equal to was estimate for this. For f of 3 of 8, where I can plug in 3.8 and then I can get that value. So I can go ahead and say y is equal to 3 times 3.8 minus 7. And I can say that I can estimate on that graph, my output would be 4.4. If I didn't know that equation of my curve, I can use my tangent super close and have that be an estimate. So my y is going to be estimated to be 4.4. Because it's a concave up shape, it doesn't matter where on my graph I ended up hitting. If I use the equation of this tangent line, no matter what, is this going to be an overestimate or an underestimate? Yeah, it's going to be an underestimate. And this is where they're going to get you. They want to hear you say why you think that's true, and you want to make sure that you include a conversation because f of x is concave up, so values on the tangent will be an underestimate. That concavity changes your answer for sure. All right, here's the function. We have the curve. It's a cubic. 5x minus 2x cubed minus 2 is concave down at x is equal to 1. So we have it concave down. So we know that it's down like a frown, like that. Find the tangent line of f at x is equal to 1. You can do this. Turn to your partner and remind each other of how to do this math when you mark it, set, go. All right, so this part here is nothing new. What's in blue is figuring out the instantaneous rate of change of the curve at that endpoint. What's in purple is figuring out the xy order pair of where that tangent and my curve meet. So if I have my curve right here, this point here that they share is 1, 1 with a slope of -1. When they say what is the estimate for f of 1.1 using local linear approximation for f at x is equal to 1, this is where sometimes this stuff seems silly, and we're learning it at an introductory level because I'm kind of like, we'll just figure out what it is by putting 1.1 into the original curve, right? Like I'm kind of like, all right. Do you want it approximately by me using the tangent line, or do you want it exactly by me using the original equation? And they're like, oh, no, stop thinking. We want you to practice doing local linearity. So if it seems kind of silly or foolish what we're doing, it's because we're learning it on a very basic introductory level, and there's going to come a time where we don't have the equation of the function, but we can still use the tangent to justify how we can get those input and output values. So we'll do it their way. We're going to go ahead and use the equation of the tangent line, and then we'll talk about whether it's an over or underestimate. So if we want to simplify this, we can have y is equal to the opposite of x. If I distribute that, that's plus 1, and then add another 1, and I get plus 2. You okay with that? So when I go to fill in my output values equal to the opposite of my input value, which is going to be 1.1 and then plus 2. So what is the estimate? We can say that f of 1.1 is going to be about equal to, what does that end up being, 0.9? Yeah? 0.9 using local linearity. I can use my input-output from my tangent. Because this is so super close to where I'm doing my x, then I can go ahead and just use my tangent equation and say that that is an estimate. Is it an over or an underestimate? Yeah, so this one's going to be an overestimate, and it's because f of x is concave down. So the values on the tangent are going to be an overestimate. All right, 3 is a much better problem because they didn't give us the original equation, but we do have the derivative. I know this is the derivative because it says dy dx is equal to that. So that is the derivative of my original function. I don't have my original function. In about 2 months, maybe 1 month, we're going to start taking the antiderivative. So instead of having the original function and breaking it down by looking at the instantaneous rate of change, the antiderivative is going to be where we're given a derivative and we have to build the original function. So until we know how to do that, we're stuck here. All I have is my derivative. So it said, consider this differential equation. So somebody took the derivative, and there it is. Let y equals f of x be the particular solution to the differential equation. So that's a long way to say this is an input-output value that we know works. So at an input of 2, we get an output of 0. So we can write the equation of that tangent line, because all we need to do is figure out the slope at that point. Turn to your partner, get your calculators out, and figure out how to do that. Go. Okay. So if they give me dy dx and they want me to find the slope of the tangent line, that's the instantaneous rate of change. So all I need to do is plug in those input and output values. So I have e to the 0 because in my equation it's e to the y. And if you look at my input-output value to 0, I'm going to plug in 0 for that exponent value. Times 2 squared minus 5 times 2. So that looks like 8 minus 10. So we get a rate of change of -2. That's my instantaneous rate of change at that x value. So then when I go to put it into my point-slope form, I can fill in what I know. I have an output value of 0, input value of 2, and a slope of -2. So when I get the equation of the line tangent to the graph at that point, then I'm good to go there. So I can then use this tangent line to approximate this value. So here's how these questions are going to look. They're going to ask you, hey, can you approximate this? And you're going to be like, oh, I don't know how I can do this. You're going to be like, wait a minute, I can do local linearity as a strategy that can help me do that. So all I need to do then is to look at this and say, okay, my output value, or if I want to stick with my function notation, sometimes that's better because it helps you keep track of f of 2.2 is going to be roughly equal to -2 times that input value plus 4. So f of 2.2 is roughly equal to, so what is that, -0.4? Did I do my math right? The interesting thing here is we can't say if this is We can't say if it's an over or an underestimate. How come?
So we don't have the original.
Yeah. Because we don't know the concavity of the original function. Without knowing that concavity, there's nothing we can do. So basically, it's a conversation where if we have an equation and we can figure out that tangent line, that xy point of tangency, we can use the linear equation of the tangent line to estimate values that are super close to what is happening here. So the tangent line of a function can give you an approximate value for points that are super close, and you want to make sure that you keep in mind that super close idea. All right. So here's some practice that I want you to do, and why don't you go ahead and let's just do one. We'll stick with that with the trig function. Everyone always wants help with that. Let's do that, and then why don't you do 1 and 3, and then I'll check back in with you, and we'll go over it before the end of class. So with your partners, work on 1 and 3. Go ahead. All right. So it's really not a whole lot different from what we've been doing. So it's just the concept of, if I can't find the value on my original function, I can use that tangent if I have things like the solution and the instantaneous rate of change. And I can use that to approximate it. All right. If I have the function 2 cosine x plus 1, and I know it's concave down on that interval, what is the estimate for f1 using local linear approximation? And then give an exact answer. So they will have you doing 2 things. First of all, using your local linear approximation for the tangent line, and then doing the actual one to see how close the 2 actually are. So if they say give an exact answer, no rounding, we can go ahead and, well, I guess we'll do the derivative one first. Was estimate for local limit. So f prime of x is going to be equal to, the derivative cosine is the opposite of sine, so it's going to be negative 2 the sine of x. So I'm going to go ahead and my f prime at this input value of pi over 2 is negative 2 times the sine of pi over 2, which is positive 1. So I get that value of negative 2. When I go to plug in for my equation for my tangent line, y minus y1 is equal to m times x minus x1. I don't think I have a y1 yet. Yes, I do. I have 0, right? No, that's the interval. So when I plug 1 into, I need to know f of 1 is equal to twice the cosine of 1 plus 1. So the cosine of 1 is going to give me 1. So 2 times 1 is 2 plus 1 is 3. Yeah? So my 3 goes here. And my negative 2 goes here. And x minus 1 is the equation of my tangent line. cosine of pi over 2. Oh, wait. Why did I plug in 1 here? It's pi over 2. Right? So the cosine of pi over 2 is 0. So 0 plus 1 is 1. Right? So that makes this a 1. Get an eraser. There, we like that better. So then my equation of my tangent line, y is equal to negative 2x, that's plus 2 plus 1 more, there's my 3. So what is the estimate for f of 1 using local linear approximation? So I'm going to plug in my x is equal to pi over 2. Where's my estimate for f of 1? So pi over 2, 1 is my point, my input output, and what I want is a local linear approximation . No, I want f of 1, right? Help me tease this out. Because I've mixed it up once, and I know you guys are at the end of the period, you're like, we don't care, we want to go eat lunch. So there's my equation. I'm estimating f of 1 using the local linear approximation at an input value of pi over 2, 1. I take the derivative, pi over 2 is 3.14 divided by 2, right? So 1 is pretty close. So an input of pi over 2 gives me an output of 1. When I find my derivative, at that point it's negative 2. But I think this needs to be pi over 2. I'm getting tangled up between my input values. There's my slope. An input of pi over 2 gives me an output of 1. So that's 2x. And here's plus pi, and then plus 1. So that output value, if I'm estimating for this, is going to be y is about equal to, and I can use this equation, negative 2 times 1 plus pi plus 1. So my y is going to be about equal to negative 2, so that's negative 1 plus pi. Is this concave down? That's an overestimate.